We're, no, 2.3, example 3, on page 57. I think that's what I had marked. Okay. And, you know, in this class in linear algebra, I have to use the, you know, the thing you set up with the whiteboard and graph board. But this morning, I went to do it on, you know, in my 112 class, which has PowerPoint. But of course, every time I do that, it goes back to presenter view, and I have to do, and it's just about to drive me crazy. Nothing you can do about it. It's just this sorry package that makes you do this every time. And then when I go back to the PowerPoint slides, I have to go back through, you know, and get off presenter view, and I thought, this is driving me nuts. And then redo my pen and redo everything. So anyway, let's pick up and go from where we were last time. Here's example 3. Solve this. Oh, speaking of which, okay. X dy dx minus 4y is equal to x to the 6th e to the x. Okay? How would you proceed with this?
Isolate a variable, or well, get variables on either side, so I divide that x over.
Okay. Now, the reason for that is to get it into the standard form for you to use the linear thing. And yeah, we don't want a function there, so we divide every side by x. Every term on every side by x. So this now becomes dy dx, okay, minus 4y over x is equal to x to the 5th e to the x. All right. Now, maybe a better way to write that middle term would be this. You tell me. Either way? Why would this might be just a tad better?
Keeps your x and your y kind of separated
A little bit. But you remember what your basic form is? Okay. All right. If you go back to page 54, equation 2. There's the form you want. Okay?
So that gives you p of x.
That gives you p of x, exactly. And the other way does too, but it just doesn't seem as obvious.
Yeah.
So that's your p of x. Okay? Now, all right. What's your next step? Wake up. No, okay.
Don't you need to find the derivative of 4 over x?
Not quite.
The integral.
Integral, okay? And keep the sign with it too. So the first thing we do is integrate the p of x dx, which is integral of minus 4 dx over x. Yeah! I say dx over x, all right, dx over dx. Dx over x, okay.
And that's not 1.
No. All right, dx over x. All right. Remember, that's a pretty easy thing to do. What is that?
Natural log of x, or negative 4 natural log of x.
Negative 4 log x. Okay.
Absolute value.
What's that?
Absolute value there.
Yeah, technically, yeah. Okay. But let's leave it off for now. What's the next thing we want to do? And by the way, this is one, I don't want to say only, this is one indefinite integral that you don't put above CY. Don't do it yet. You'll take care of those later. So leave it just like that. Okay. Okay. What you're going to do next is do an e to the this, remember?
So raise it to e. Or
You do want to, but not yet. Because we are going to raise it to the e, raise e to the this, or whatever. Use your rule of logarithms. Remember how that goes? This is the same as the log of x to the minus 4. Remember that rule? Property of logarithms? Okay. Now raise that. E to the integral p of x dx, which is what we've got here, now becomes e to the log of that, which is what? E to the log x to the minus 4 is x to the minus 4, right? Okay. So that's going to be your multiplier, right? All right. And what do we do with it? Every term on both sides by this. So this will be x to the minus 4. That is a 4 there. It's an ugly looking 4. Dy dx minus 4x to the minus 5. Y, okay, is equal to
x squared. E dx.
I think it's just x, isn't it? Yeah, it started out a 6, but we divided by x, and then became a 5, and now, yeah.
I was looking at the wrong. I was looking all the way back to the top instead of to the last.
Okay. Now what? Okay. Why did we do that anyway? Why was the whole process of multiplying by e to that? It was called the integrating factor. You want this to be the result of a product rule, differentiation of a product rule. So this would be d by dx of okay. Well, here's a okay. Derivative of this is that, right? So this is your u dv, and this is the
DUV.
yeah duv, du, right? So this is one, and that's the other. At least that's the. Let's do that as our first guess. X to the minus 4y. Okay? Now, before I swear to that, let's make sure this is, let's do this. Let's take the derivative of this. Well, the derivative of this would be minus 4 e to the x to the minus 5 times y. Sure enough there. Plus x to the minus 4 dy dx. Yes. So that is d by dx of that. Okay? And this is equal to x e to the x. All right. Now, we write it in differential form.
Yeah.
D of x to the minus 4y is equal to x dx. Xe to the x dx. I get so looking forward to that. I left off a term. Okay.
That's it.
Okay. X e to the x dx.
That's it.
Oh!
Go back.
Yeah. All right. Now,
I like how
we'll integrate this and integrate that, right? And the integral of a differential is the function. X to the minus fourth y is equal to, and what's the antiderivative of that? How might we do that?
Well, it's not just the e to the x, but you have to make something.
Right.
Would it be a product?
Not
You'd have
quite.
something added or subtracted together, but exponents wouldn't change.
When you have a product, you can think of each of these being a part
Oh, you can-
of your integrand. And we want to integrate by parts. Okay. I just made that up. But yeah, integration by parts is what we do. Now, I'm running out of room rapidly. So, is it all right to go up and erase the top line?
Yeah.
Okay. Sorry about this, but I write all over the board. And I wish this would give me the entire board, but it has this big border at the top and a big border at the bottom and little borders on the side.
That also makes it where you can get to your pen easy, though.
Yeah, I know. That's the upside. But most of the time I could still get there. I might just lose a little bit. Okay. So we're going to integrate this by parts. How does that go? In fact, I think I want to eliminate this over here because I like having this room here. We've already done that, so I think we're okay to get rid of that. Okay. So how do we do integration by parts?
Oh, yes, that's the dx and the d, or the x, or the u and the d.
Yeah, let u equal what? Okay, now, here's how we do
It's
it.
gonna get, this one's gonna get more complicated, or no, less complicated. The other one's gonna get more complicated.
Well, okay. You want to differentiate the thing that has potential to be more complicated because usually integration makes it worse. But if you have one of these you can integrate and it doesn't get worse, like that one, let that be your D. Okay. So the U is going to be X and dV is going to be e to the x dx. Okay? Then, what's your...
It'd be 1 for the du, right?
Well, du is equal to dx, 1 dx. Okay, dx. And v is equal to e to the x. Fantastic. Now what do we do?
Multiply the u and the v, right?
Okay, multiply u times v, and that is x e to the x. I swear. Okay. Okay. Minus the integral of the bottom line. Yeah. Okay. Minus e to the x dx. That one is very easy. Okay. So this is x e to the x minus e to the x. Okay. And that's what the left-hand side is, x to the minus fourth y. Now this one we can actually, solve for y by multiplying everything by e to the fourth. Okay, so this would then y is equal to x to the fifth e to the x minus x to the fourth.
Even though that's a negative,
What's that?
even though that's a
Okay, we're multiplying both sides by x to the fourth.
Okay.
And that would make the right-hand side just y, the left-hand side this. Okay, and you can write that several ways. I mean, that way is just good. And at some point, we do need a plus c. Now, whether that's the best place to put the plus c, I'm not sure. In fact, they're suggesting not. They suggest to do the plus c at the previous step here, and then when you multiply, then this will give you plus c x to the fourth. Okay. And I guess that makes the most sense because this is the side you're integrating, this thing right here. This doesn't. You can combine the two constants. But here's where you put your plus c. After you do this integration, which was done here, then put your plus c, then multiply by that. So probably is the best place to go.
So I can write it so e to the x plus c instead of
What's that?
so e to the x plus c.
Well,
Or are you just adding it like
okay. It's
plus
this integral here, which is this, plus c. This
C.
integral became this line plus c.
that's
Now, it's not x plus c.
yeah, okay, that's what I was confused.
Yeah. X e to the x minus e to the x plus c. That should be down here. I just didn't read the right. Let me erase it. So for people who are watching at home, that could be, that aren't able to ask the questions. Let me, it didn't erase. It does that about half the time. I click on it and then it doesn't come through. Okay. I click on it and the pen doesn't show up. Okay, now I think we got it. Plus c, and that's equal to your x to the minus fourth y. Okay. So this is one that you can write, and what they call this the general solution. Now,
That makes sense because you wouldn't have the side that you're integrating, and once you get through integrating it, you add plus c, and then you start messing with both sides of the equation.
yeah, okay, yeah. Yeah, the thing is, get it in standard form first. Okay. If it's a linear equation, okay, meaning your dBs only are to the first power, however many you have, your y's are only to the first power. You don't have a y prime times a y. You don't have cross terms in there. And then your x can be anywhere else. Get that in standard form, which means your dy dx cannot have a coefficient. So divide by any coefficients you had. This one had one. And then once you've got that, identify what is your p of x. I've already erased it, unfortunately. And it was minus 4 over x. That was our p of x. Integrate that, okay, dx. Find out what that is, and simplify it as you need to, because the next step we're going to raise it
It's
e to that thing, that integral. And so since we had a minus 4 log x, it'd be better just have a log x and move the minus 4 to your exponent using the rules that you can. And then that gives you just a pretty simple multiplier, e to the minus that fourth. Then you do that to both sides of the equation, recognizing then that produces a product rule always. That's why we're doing it. It does produce that. Identify what that product is. It's the undeebled here, that one, so that means that's the undeebled here. Good way to express it. So here's the undifferentiated function here, there's the differentiated, undifferentiated there, so that's your product. That the derivative of that is indeed pat. So then take the integral of that and write it in differential form. And you're integrating, well, write it in differential form with the dx and get some steps here. But your where are they? Yeah, here it is. Okay, this is differential. That's differential. Integrate both sides. The integral of the differential is the argument, and then the integral of this required you, in this case, to do integration by parts. It may have been partial fractions. It may have been just a straight integral. It may have been look it up in a table. It may have been do numerical integration. Something, but that's just going to be an integral there. And when you do that integral, that's usually the place to put it in plus c. Definitely not when you're integrating. Don't mess with it there. Wait till this point. Put it in plus c. And then if you have to do anything, simplify like we did here, the c gets in on that. Okay. Now, the one thing that you had mentioned, not doing the absolute value. They took care of that earlier in the thing. They said dividing to get the standard form, from this we identify p of x equal to, minus 4 over x. F of x is equal to x to the fifth e to the x. And further observe that P and F, now here's the thing that they're required to be. They must be continuous. Okay? So, that's why we have to leave out the 0, because the 4 over x, which I've erased already, oh no, here it is. You can't have it as 0 here. Okay? And since you can't go across there, it can't include 0, we're only going to take the right-hand side. X greater than or equal to 0. That's what enabled us to do this without the absolute value.
And it went out anyway because you raised the t. So.
Yeah, but it still has to be there because it was a requirement here, so it will be a requirement there. But actually, when we got to this form, we know x can't be 0, and the interval can't include 0. So you choose either the left-hand side or the right-hand side. We go with the right. We like being in positive territory. Because your integral must be continuous. Okay, the integral must be continuous. And cannot include 0. So, that's why it says, in case you're wondering why the interval 0 to infinity is important, in example 3, can't talk. Read this paragraph and the paragraph following example 4. Except in the case in which the lead coefficient is 1, the recasting of the equation 1 into standard form requires division by a1 of x. Values of x for which a1 of x equals 0 are called singular points of that equation. Singular points are potentially troublesome, specifically back in the original thing, number 2, if the p of x formed by dividing a 0 of x by a 1 of x is discontinuous at any point, the discontinuity may carry over to solutions in the differential equation. So basically what we just said. So,
a few more words.
Yeah, a bunch more words. Okay. So let's erase, down here. Erase all this. Do you have it? Okay. Erase all that ink. And let's do example 4. Another general solution. Find the general solution of x squared minus 9 times dy dx plus xy is equal to 0. Okay? So what's your first step?
Well, you gotta get dx by itself.
Right.
So divide 0 by that and divide xy by that.
Okay.
So,
And I'll just leave off dividing 0 by, I've done it. Done.
yeah.
Okay.
Did all that in your head.
Okay, so this then produces dy dx is plus, all right, and again we do this, x over x squared minus 9 times y is equal to 0.
I would take the integral of x over x squared minus 9.
Okay. Let's pause just a minute here. No. Trying to see if there's a way to separate variables. Yeah. Okay. Now, I think they want us to do the other way, but why not this? Dy dx is equal to minus x over x squared minus 9 y, right? And then write that in differential form and divide by y, and you would get 1 over y dy is equal to minus x over x squared minus 9 dx, and integrate both sides. Okay. Now, it's up to you which one of these you use. Usually, I find separation of variables might be just a little bit more straightforward, but
Yeah,
maybe
if
not.
you can do it.
If you can do it. So let's see if we can. The thing is, guess what? You were going to wind up integrating this anyway. That was your P of X. So that's what would have been your first step anyway. So nothing lost there. And you're going,
Natural log of y on the left.
yeah, this is natural log of y on the left. Okay. So this requires,
Would this be the partial fraction?
yes, exactly. Okay. That was my next question, and you beat me to it.
I'm glad, because usually I don't.
What's that?
I said I'm glad, because usually I don't.
Okay.
So that would be. Alright, so we gotta break up that denominator, right?
Yeah. And how does it factor?
X minus 3, x plus 3.
Right. All right.
Throw one up.
So we want to write that as, usually they like capital A's, I don't know why, a over x plus 3 plus b over x minus 3.
Alright, and we multiply by the original denominator.
Right. That gives you minus x is equal to a times,
8 times x minus 3.
no plus. Oh wait, yeah, I can't read my own writing. I was thinking that was the minus there, it's the plus. Okay. Okay. X minus 3 plus b times x plus 3. Okay.
Now we gotta use the trick.
And what's the trick?
Let x be 3.
Okay. So this would be negative 3 is equal to, that goes away, 6b. Okay. That means b is equal to negative, second? Yeah, negative 1/2. I didn't know if you were saying 0.5 or 1/2. I can't hear well enough. Okay?
Why turn it into a decimal?
Yeah. Then the,
Let x equal negative 3.
okay, so then that would be 3 is equal to
Negative 6a.
negative 6x plus 0. Okay? So this would then have x equal, huh?
It'd be a.
Oh, yeah, sorry, a. Okay.
Go back.
Okay, so that means a is equal to negative 1/2 also.
One more. See, I'm glad I put that extra one in there.
All right.
Ended the PowerPoint.
All right. So, Yeah, thank you very much. This would be, both of those are that. That would be minus 1/2 integral of dx over x plus 3 plus the integral of dx over x minus 3. I just pulled the negative 1/2 out because it was the same on both of them, I think. Okay? And what would that be?
Natural log.
Of?
X plus 3. Sorry, right.
Yeah.
Plus natural log of x minus 3.
Okay.
Equals natural log of y.
All right. And that's the natural log of y.
And we don't want to distribute the hell out and raise everything to u.
Okay. Yeah, no, we do. We want this to go over here too. And I'm running out of room. It's already tried to click out on me a couple of times. So I don't know where the best place to lose it is. I'm going to hang on to the original, so I'm going to lose this one. And the eraser is very slow right now. Huh?
I was going to say, we've already simplified what's right below that.
Right. All right. All right. Yeah. So this is log y is equal to log of, okay, negative 1/2,
Raising it to the
right, log of, I'm going to come back and, I'm going to hope this works, okay? I might have to come back and change minus 1/2 plus log of x minus 3 to the minus 1/2. Now the thing is there, we could have left the minus sign. Oh, no. I think this is what we do want. Because this is going to be the log of, I could have done the other way now that I think about it. I should have done it that way. We're getting there. The other property of logarithms is that's the same as x plus 3 to the minus 1/2 times x minus 3 to the minus 1/2. Okay? Because of the sum of logs is the log of the product. Remember? Okay? So, now that we've got that, we've got a log on one side and a log on the other side, so that leaves us with, oh, no, wait. Where is our constant? Where was the best place to throw that in? Probably right down here, and we would have said plus log of c. Yeah, you can make it anything you want to do. Why not? And then that way the c gets multiplied by these two. Right. And then when you take the log of the e of both sides, you get y is equal to y is equal to c times 1 over x plus 3 times 1 over x minus 3. Oh, these are square roots. Yeah. Or c, okay, whatever.
And when whenever you put it there, at the, where you put the C, natural log of C,
Right.
we wouldn't have to worry about the exponent for that when we bring that 1/2 in.
Yeah, okay. Actually, let's do the, we could have integrated that and had those in there already, yeah. So have the negative 1/2 there
Instead
and
of-
there.
Yeah,
And
instead
then
of
do
holding
plus
it.
one. I think. Let's see how they did it. You can write, it just, how it's going to make that the easiest for you to do.
As long as we came to the same conclusion they did.
Right. Now, here's the deal, the one more thing here. You can multiply those two square roots together and give you C over the square root of x squared minus 9. Okay? And I think that's what they wound up with. But they tended to leave off the constant altogether. Oh, no, they threw it in at the end. Okay.
So, then at the end.
Yeah, so that's exactly what they got.
That's funny.
Okay. But understanding this, that x equal 3 and x equal minus 3 are singular points of the equation, and every function in the general solution is discontinuous at those points. On the other hand, x equals 0 is a singular point of the differential equation in example 3, but the general solution for that okay. A lot of blah, blah, blahs here. Here, what you have to do is mentally do this. Break this. This actually has, it's the same solution, but it's 3 different pieces. Either x less than negative 3, or x between negative 3 and 3, or x greater than 3. This solution works for all those, but not at the other points. Okay. And there's a part of me that sort of rebels against that a little ways. If x is all negative, no, I'll take back what I just said. X cannot be less than negative 3. It cannot, because if it was, this is not defined. And by the way, that's not defined either. So X can't be that, okay? X has to be greater than negative 3 then, but this doesn't allow it to be anything greater than 3. So I think by the virtue here, this one is really only defined for x greater than 3. Can't be equal to 3 because we can't take the log of 0. And it can't be in between because even though this would be okay, that would still work. So I think you have to require it to be greater than 3. Now, they don't actually say that here. They say those are singularity points. Yeah, I agree with that. But it says, and every function in the general solution is discontinuous at those points. Yes, I agree with that. On the other hand, the general solution this is going back to example 3. So they leave you hanging there, and I generally don't think, because of how we did this, you can ever allow x to be less than 3 or even between -3 and 3, or less than -3, ever, or between 3 and -3, -3 and 3, or I think you almost have to have the x greater than 3, I think. I can't make it happen in my brain without it being greater than 3. They don't actually say that here. They said on the other one it had to be greater than 0, but on this one they don't say it has to be greater than 3. They just say these are singularity points. Yeah, I agree with that.
It says it can't be 3. It can be in between 3 and 3.
Okay. Actually, what they say is it can be less than -3.
Let's see. You're talking about where it says, although P
It
is
says,
continuous.
no, you see up there, right before the blue general solution, that sentence that starts there, integrating both sides of the last equation give blah, thus for either x greater than 3, I'll buy that one, or less than -3, that's the one I'm having trouble swallowing. Okay?
In the last, I don't know, earlier probably it's good. At the end, I guess.
What's that?
Just the general equation, if you plugged in something less
Yeah.
than -3.
And here's why they say that. Your original problem, you certainly don't want that being 0, because it wipes out all meaning of the problem. So that's one reason you eliminate -3 and 3. That would make that 0. But when you divide by that, basically your problem is let's go to this. Forget that. Let's go to this one. This is only defined for positive numbers. Okay? This is what they're doing here. If x is between -3 and 3, then in both of those cases, when x is -3 or 3, this becomes a 0. Okay? If x is in between those, then say a 2 or a 1 or a 0. You're taking the square root of a negative number. You can't do that.
Yeah.
But if you had
It's just
x,
I think it's just saying that it's outside negative.
exactly. That's what they're saying. But I'm saying, how can this part be in there, or this part, for x less than -3? I don't see how you can do that. Wait. It's 1 over. Yes. Yes, sir.
I had just got my financial aid award. They wanted me to come talk to me. I had to get my books and stuff now. I was trying to see if I was going to be able to catch up on my work that I had to do.
Okay. I'm in class right now. Okay. Out of class at 12:15. Will that work for you?
Yeah.
Okay. What class are you in?
I'm 100.
100. Okay. No one told you not to come to class, did they?
I had to move books and stuff.
I understand that, but you could have been coming to class still. So I wish you had, but yeah, we'll talk about it. But let's talk about it after 12:15. Yes, you can catch up to answer your question. Yeah. See, walking in on a class course may have looked like this was tutoring or something, but just looking at the final answer, it looks like, yeah, as long as x is less than -3, this makes sense. And greater than +3, that makes sense. It just can't be anywhere in between. But you see, look at the steps I had to get there. This is the square root of this, and that would indicate x has to be greater than a -3 for that to make sense. And this says it has to be greater than 3. So I don't see, I'm having trouble seeing how you can eliminate, just ignore those parts and just look at the final answer. Yeah, the final answer says it has to be.
Because that would give you imaginary stuff.
Before you got to the final answer. Yeah. And I don't know that you can just ignore that. They're saying, indicating or suggesting you can. You just look at the final answer and say, yeah, that's good for here. So maybe it's okay to. Okay, no, let's take that back. That's because of the way we did the problem.
They did it
the other way, but you still did partial fractions, I think. Didn't they?
They have the natural log of x squared minus 9 in there. There's the e.
Oh, you know what? Silly us. We did partial fractions when we didn't have to. Okay? Right? Aha. Have I erased the part that I need to be looking at now?
The x over x squared minus 9?
Yeah, we didn't need partial fractions for that. Substitution would have worked there. Okay. Duh. Okay.
We just like work.
Yes, we did. Well, you needed the review on that for the math team. Right. No, okay. So, no, that's where we messed up. Let's see, though. X over x squared minus 9 dx.
What, x squared minus 9?
Yeah. Yeah.
2x dx?
Yeah. Let u equal x squared minus, yeah, you already said that. I wasn't listening. Let u equal x squared minus 9 du is equal to 2x dx. This is so slow. I mean, it's just incredibly slow. Okay? And so x dx, let me, since it was all totally unnecessary, I hope I can remember what I was doing here. There's a real big part of me wants to just erase all of it, okay, and start back over. In fact, I think that's what I'm going to do. I know we had started doing it right, but goodness gracious, this is slow.
When was the last time you restarted your computer?
What's that?
When was the last time you restarted your computer?
This morning?
Oh, wow. And this class ends at 10:45.
Yeah.
Just making sure we still got good enough time.
What's that?
I was just making sure we still have plenty of time.
All right. What time is it now?
10:25.
Okay. Okay. Let's start this over where we should have been in the first place. Okay.
That's next.
We had that, and we did dy dx is equal to minus x over x squared minus 9y, and then dy over y is equal to minus the integral of x dx over x squared minus 9. That's where we had. And we proceeded to do this part with partial fractions, which was totally unnecessary. I mean, it worked, but it probably introduced some more complications than we needed. Let's just do this one. And as you said, let u equal x squared minus 9, then du is equal to 2x dx, okay? And du over 2 is equal to x dx. Okay, so now we have, let's go on and integrate the, well, okay, we'll leave it for now. dy over y is equal to minus 1/2 the integral of du over u. Right. So this is natural log of y is equal to, like you said, the negative 1/2 the natural log of u. You put it on top, so that's log y is equal to log u to the minus 1/2, and then plug back in what u is. U is x squared minus 9.
Oh, because you had to integrate the left side too. You didn't have to log y.
Yeah, that's what I did there. Yeah, I'm sorry. Okay. And so this would be y then is equal to 1 over the square root of x squared minus 9. Yeah. So you get there without having to do a log of anything else. And you can put your plus c in there. That's fine. Okay. I did a couple things at once there.
And they also,
I plugged this in. This is the square root of u. U was x squared minus 9. So this is 1 over square root of x squared minus 9 plus c. And then
that's equivalent to y equals c over x, the square root of x squared minus 9.
are actually the way they did it. And it really doesn't matter. Let this be a plus log c here, and then do a cu. So that's how they did it. They did the plus log c here. Okay. And then this would be, it's all a matter of where you want your constant to be.
My question is,
Right.
on, like, let's say a test, would you take that ending answer plus c, or would you want the answer negative 1/2 plus log of c?
Say that one more time.
Would you want the plus c, like 1 over square root of x squared minus 9 plus c, or have c in the numerator, or does it matter?
It's neater here. That's all.
That's good.
It can be anywhere, but this works. This makes it c times that.
So kind of more so make sure it's there, don't really sweat as much of where exactly it's at. as
That's
long as it makes
basically
sense.
it. But this makes your family a lot more identifiable, you know. So if you can get it lumped with that, that's good. And this gives you, and that's exactly what they have. Now looking at this, don't worry about anything else. That denominator can't be 0, and you can't take square root of a negative number. So not being 0 eliminates plus or minus 3, and then it can't be a negative
It
number.
doesn't matter how
It's-
negative it is. It's
Right.
You're squaring that.
It just has to be more negative than minus 3, and or more positive than positive 3. Anything else in between there, you lose. That becomes negative and so on. And it can't be plus or minus 3 because that would make the denominator 0. So it has to be opposite. So, yeah, dumb me.
The world
Okay.
makes sense again.
Right. All right, let's do example 5. Do you think we have time? Okay. All right. Solve this. dy dx, okay, plus y equal x.
And it has the y0.
And y of 0, this is initial value problem. Y of 0 is equal to 4. Okay.
That's set up really nicely.
It sure is. I mean, they've done all the preliminary work for us, so what have we got yet to do?
Put it in differential form.
I don't think we can quite do yet because this isn't separable. If that was a 0 over there on x, yes, that would be. It's not. It's an x. If you subtract y, you got a difference. You don't have a product. So you can't separate. But what's your... Sorry, I can't talk. For some reason, I've been eating frogs. I got a frog in my throat. So what is your p of x? 1. So that's what we do. We integrate 1 dx. And that's equal to x. Okay? What do we do with that? Second? No, raise it to the e. Don't forget that step. Now multiply it by everything. So that gives you e to the x dy dx plus e to the x y is equal to x e to the x. I'm going to do it that way so it makes it easier to see to me. I think y e to the x would have done better too, but I'm used to putting that in front. Okay, this side we expect to be, and it better be, of a product, derivative of a product, exactly. And what would that be then? D of e to the xy. Now, at this point, I like to go back and check. The derivative of that would be e to the x y plus e to the x dy dx. And that's exactly what we got. Okay? And that I'm doing my differential at the same time, x e to the x dx. Okay? And when you integrate both sides of this, you now have e to the xy What's that?
Can't remember what the integral is.
Yeah, it's partial. It's integration by parts. And it comes out x e to the x plus e to the x. Okay?
And we'll just do that off.
Okay. But you can always check it by taking the derivative of this and see if you get that. Right? So the derivative of this would be x e to the x. Seems like maybe that should be a minus. Is that right? I believe so. Because if you did x e to the x plus e to the x, then this would have to be a minus e to the x, I think. I don't remember it being a minus, but it must have had to have been. Because when you take the derivative of this,
Yeah, it was.
Okay.
It was minus x e to the x minus e to the x because
Right.
you're supposed to subtract the bottom.
That's right, yeah. Right, yeah.
You're
So-
not completely.
But that's why checking always helps. Because before checking, you wind up with 2 e to the x's, and that wouldn't have worked.
Yes.
But if that's a minus, that would work, and sure enough, that's correct. Okay? And at this point, I think I would say a plus c. Okay. Or do I want to say plus e to the c? I don't know, and I really don't care too much.
C to e to the x. Do we need to separate the e to the x and the y?
Say again?
Do we need to get y by itself?
I can't.
Do we need to isolate y?
Well, what I was going to say, without the c in there, you would just multiply everything by e to the minus x, and you'd have y is equal to x minus 1. Okay? Don't think you could do that. Okay? So,
Divide by e to the x?
let's do that. That's just as good as anything. And you have y is equal to x
Minus
1 plus, you want to leave it as plus c? Or does that need to be c over e to the x? I think we need. Or c e to the minus x. That might, I don't know which is easier for you to do. Okay, but now what we're going to do is do, when x is equal to 0, y of 0 is equal to minus 1 plus c over 1, right? And this is equal to 4. So this means c is equal to 5. Right? Okay? So then we can say, which is it? Y is equal to x minus 1 plus 5. 5e to the minus x. I'm going to write it that way. I don't know if that's how the book does, but it just seems like it's easier to write that way. Well,
That's how they write it.
is it? Okay.
Plus 5e to the minus x.
What's that?
Plus 5e to the minus x. That's
Okay. And, okay. X minus 1 plus 5e to the minus x, right. Okay. Now, and where is that good? Everywhere. Everywhere, because x's, the domain of x's, all real numbers. 1 certainly is all real numbers. E to the minus x, all real numbers. No sweat anywhere here. So that's good everywhere. And I don't think there was anywhere in the working out of the problem that we were introducing anything that would have been a problem either. Okay. Now, as simple as that seems, I don't know if it seems simple to you or not, this would be for c equal 5, that was the dark blue line there, that would have been your function then. Okay? All those others are your families of functions. C is equal to 0. If you would have gone back into that, that'd just been y is equal to x minus 1. And sure enough, that's a straight line, slope of 1, and y-intercept of minus 1. That's your c is equal to 0. Okay? And then for positive c's, you have, I don't know what shape you would call that. They kind of look like hyperbole a little bit. For c less than 0, I guess these are really broad hyperbole down here too, but I don't know. I don't know. They're not hyperbole, either one of them, because they have exponentials in them. So they're some form of an exponential. Okay. Let's see what they say about it. The figure obtained by aid of a graphing utility, thank you very much, shows the graph solution 8, the one in dark blue, with the graphs of other members of the one parameter family, integral numbers anyway. I don't know which ones they did. I'm guessing the first is c is equal to 1, c is equal to 3, c is equal to 5, and the next one c is equal to 7. And probably did a minus 1, minus 3, minus 5, minus 7 too, but I don't know that. Okay. But the straight line is c is equal to 0. All right. The asymptotic behavior of the solutions is due to the fact that the contributions of ce to the minus x, as when that's not equal to 0, become negligible for increasing the values of x. We say that ce to the minus x is the transient term. So in other words, this term here, this one here, or this one here, this one with 5 in there, let's call that ce to the minus x up there too. For very large values of x, this loses its meaning. And then you you basically get down to this, okay, and that's either large. No matter what the C is, this is going to go to 0 for very large. So that's why for very large x's, very, very, very large x's, everything's coalescing to the line y is equal to x minus 1. But for smaller values, now they take on means, okay? And certainly when x goes negative, you have an exponential function then, because now it's e to the minus of a minus number, which is e. So those get extraordinarily big, okay? Now if c was negative, that just flips it over, basically. But yeah, that's this part doesn't make a lot of sense. Well, certainly, as x is approaching 1, this part doesn't make any sense, and this is looking just like an exponential function.
E is raised to the negative x.
What's that?
E being raised to the negative x minus I don't know. It's just
Well, I think we don't want to overanalyze. But that's why they call this a transient term. For very large x's, this is meaning, and then that becomes your solution for very large x's. They all coalesce to that. Okay, now, discontinuous coefficients. In applications, the coefficient p of x and f of x and the original function 2, differential equation 2, may be piecewise continuous, okay? In the next example, f of x is a piecewise continuous on 0 to infinity with a single discontinuity namely a finite jump discontinuity at x equal 1. We solved the problem in 2 parts corresponding to the 2 intervals over which alpha is defined. It is then possible to piece together the 2 solutions to x equal 1, blah, blah, blah. Okay. Do we have time?
10:43, 2 minutes.
2 minutes? Okay.
No.
No, we don't have time. So we will pick up next time with example 6. You can go back and read that wonderful little paragraph. This guy's writing, to me, leaves a lot to be desired. Okay. It's not what I say really clear writing. Okay. Let me give you a few homework exercises. Let me go to the back and make sure these are covered.
Yeah,
This is 2-3. 2-3. I'd say any of the odds 1 through 23, and just a quick glance, looks like all those are covered. And then any of the odds 25 through 35, let's see if those are covered. 25 through 35, it looks like all those are covered. Any of the, either 37 or 39. Wait a minute. Okay, no, forget those. Just go through 35 because those are the piecewise functions, continuous functions, and we'll do those next time. All right, so we'll finish 2.3 next time, and then we'll go to 2.4, which is exact solutions. Okay, and no, I'm sorry, exact equations as opposed to exact solutions. All right, and I forgot to mark you here, so I think I will because you were here most of the time. Okay, and boy, this is just amazing. Ashley not here, Victor not here, Javon not here, and Rena, I still put her as not here, but I don't know if she's going to make it or not. Okay. I'll give the projector a little break, and I will erase all ink from the slide. And I'll end the